Hello everyone, we are Olympus Solutions and this is our product H Mobile. My name is Bryson Miller.
I'm Karina McDuffie.
I'm Danny Fan.
Matthew Spickelmeyer.
I'm Tawana Massini. So our objective and concept hasn't changed since last quarter, but for our approach, there has been a few new approach. For the designing a compact and a reliable lifting structure, design a powerful, effective lifting mechanism, design a versatile, stable driver system, design a software application for remote control, design a grabber system to handle items, use a 12-volt battery to supply all systems. And for our budget, we have spent $220 so far, and we expect to spend $1,200 in the coming months. Our product, H Mobile, will be able to have mobility, grab items, and to bring back onto the platform, lift the load to a maximum height of 1.5 feet, detect obstacles around, be operated remotely. This is our functional specifications for safety, and these are our specs for. These are also our specs for safety, and this is the spec for the cost. This is the spec for physical characteristics of the size of the robot. And then these are the specs for control response and the specs for the mechanical configuration.
Alright, so here's our updated electrical block diagram. This is every component that receives electrical power or signal or both. As you can see, we have several PCBs, one of which is for all the subunit microcontrollers, providing instructions to things like servos, motors, sensors, and LCD screens. And then we also have some power distribution and power management boards. We are running all the power off of a 12-volt battery, but we will be using a 24-volt boost converters, two of them actually, and 5-volt buck converter to run power to all our USB powered devices as well as to our 24-volt stepper motors. The battery will also be monitored by a shunt resistor with some current sensing to address state of charge and power output at any given moment. So here's the wiring diagram. So as you can see, here's that subunit microcontroller board, and then we have a power management PCB which is flowing all the power for the design. That gets distributed into a 5-volt converter and then two separate 24-volt converters. This 5-volt converter provides power for several motors at their locations, but then also for the Raspberry Pi 5 and a USB powered hub that will in turn provide power to all the microcontrollers and as well as the LCD touchscreen. Each of the motors is controlled by a motor driver that receives signal from one of these boards, but then the motor driver is connected to the power from the 24-volt output supplies. And the rotary encoders will also be attached to the drive motors, and those will receive signal and transfer that to our board. So here's the schematic for the boost converter. This is for a 130 watt, so 24 volts at 5 amps. We will have two of these because our peak power output expected for any given 24 volt system is about 240 watts. As you can see, there's a main boost converter with a lot of filtering capacitors. These are some screw terminals, which you'll see more clearly later, and some voltage setting. The battery monitor circuit consists of this INA226 chip, which receives a voltage reading off of a shunt resistor that's 3 milliohms, and it will read that and calculate power and send that over serial interface to one of our controllers. We also currently have a fuse in here for circuit protection, but there will be added emergency shutoff features later. Here's the basic PCB layout for one of the boost converter boards. This is the footprint for where the main boost converter module will be. And then you can see screw terminals will provide secure connections for all power outputs. then for the battery monitor, we have the same screw terminals on either end, a large shunt resistor here, and all the power will primarily be going, this is the fuse holders, and here's the shunt resistor. So all the power will come in, go through the fuse, go through the resistor, get sensed by the chip, and come out.
Coming up to the software and firmware block diagrams, we have Raspberry Pi running the ROS chassis as the main programs, and in the ROS chassis operating systems is running a program called ROS2 Control. This is where the hardware interface interact with the hardware, the rest of the hardware, but outside of the ROS2 control is being contained in ROS2 chassis. We have several libraries using for talking to the ESP32 that indicating the informations, and also to publish the data that we collect from our sensors to our native Linux computer for simulation purposes and testing purposes of the robots. And then for simulation, we have our RIS2 and Gazebo simulations. In our RIS2, we integrate like monitors for camera if we use by the software teams that we are collaborating with, and nav to control, just to track down the location of the robots. Further on, we will have the ROS2 control, as I say, connect to send signals, velocity set point to automatic controllers, and we have the drivers will be driven by an Arduino Nano. It will have an IMU built in, and then this will handle PIE control to do differential drive for the drive system. And then we also have the lift. This lift will be an open loop lift for lifting, but also enclosed with the ultrasonics. We planning it to be a PI, but it's not yet determined for this quarter. And then we also have grabbers functions. Grabber functions is right now designed as an open loop for the extender, because we are expecting the stepper motor to do by step pulls because it's just extending, and then we will do a PID control loop for the servo to grabbing with the force sensor. So this is how the structure of the programs in general, including firmware, you can see right here, and software are from the source and beyond. So firmware will contain the Arduino code and machine code for ESP32 and Arduino Nano. It will receiving command from ROS through serial bus with USB, and then we have source for software with the package. We wrote the differential drive Arduino package to control through ROS control, and then our main package Minibot is we have every instruction in there, including simulations instructions and logged in with commands. Every setup is in Minibot, and then serials handling this package handling every information flowing in the stream of USB, and SLIDA is in case the software team are using any kind of localization like camera or whatever. And TwistAmber is package for converting, translating the command sending from the controller, like that we have like from application from the phones, translate that so that ROS2 control can understand which directions to go.
So this is our mechanical block diagram. We've got the frame right here in the middle. We did include the electrical components, the physical electrical components, and most of those are going to be mounted pretty much right to the frame, or they're going to have a mount that is mounted to the frame. We've got our three subsystems: the drivetrain, the pulley system, and the grabbers. And those are all built out with the mounts that we'll need and all the moving parts, of course, including the motors for each respective subsystem.
So some mechanical drawings that we wanted to point out one was the grabber arm. One concern that we have is the manufacturing price for out of house, since we plan to send this design to Send or similar companies. So we're keeping the price in mind when we do this. Another one is the grabber assembly, specifically with the tie rod end, making sure the length is a good length to make sure that the movement is smooth and also still stable and not risk of failure. And then I wanted to point out that our platform for the handling the boxes will most likely change as we build our H-Mobile product. Strictly because as we start building, we might have to adjust to something that we did not plan for, and so the track mount as well might change.
So this is the frame, just the bare bones, and you can see it sticks out in front here like force, and this is going to be the part that surrounds the platform. So the platform is going to be sticking out almost twice as far, but we want it to go out this much, and that'll keep us as stable as we need to be. And then this back part here is going to house all of these things: the drive motors, the battery, the terminal, 4 terminal blocks, 2 power supply boards, power management board, subcontroller, and the ultrasonic sensors. So we have 17 inches width here and 6 inches length, and we're going to have the drive motors here with the wheels like that. And then you can go to the next slide, please. So this rough box that I drew is represents 17 inches wide by 6 inches long. And so you can see the drive motors, and then this red part is the battery, and then power supply board, power management board, subcontroller, terminal block, the terminal blocks, and the drive motors here are going to be set down into the frame. So the battery and this pulley motor are going to be on top of the drive motors, and then all of this stuff will fit in between the 2 drive motors. And so this is the drive motor. This housing is going to change. This was I just took the two of the walls off to make it easy to view and access, but that's going to change so it will fit in the frame well. And one of the things that we're considering with this is this piece right here. So all of this, we have a 3D printed prototype right now, and it's good and strong except for this part, because this is going to need to take all the torque coming straight from the motor shaft into the hub. So that's this part right here. And so as the motor turns, all that torque is going to be going through here and turning the wheel, which is going to be bolted onto here. So we're going to make this out of either steel or aluminum bar stock, and it'll be a pretty easy shape to turn, but machining these holes and just getting it where we want it as far as strength and also accuracy, that's going to be one small challenge.
So for the electrical side of engineering analyses, we've had a couple changes, but not too much. So the motor torque analysis still holds from previously, although we may update it at some point with our new scaled model. The maximum power requirements, we at one point did a large estimate of the powers. Now that we have scaled our design down to half scale or so, we have lower torque requirements because we have lower load expectations. So that has facilitated a little bit of flexibility in our power system design. And we have designed a new one, and you've seen it. We also have some analyses to demonstrate soon about the control PID and some measurements that we're taking for that.
mechanical analyses, we analyze the motors for the grabbers. If the platform has an incline of 10 degrees, then each motor for the grabbers will need 0.4062 pound-feet. And the motors that we have currently can supply that. And then we redid the FEA analysis on the grabbers because the grabbers have changed drastically from last quarter's design to now, and it passes the FEA.
And the frame is gonna be largely the same as the one that I modeled last quarter. It's just scaled down by half, but still using steel square tube for that.
As we were doing control PID analysis, because we create a closed loop control for the drive systems, we right here just, because PID in its nature is just test and drive, so that we had result in these constants in the systems, and then these are the graph of the set point in orange, and then the response in blue, and you can see that the overshoot is about 26%, and then the steady state is within 10%. So it's not yet very good, but the motors itself was driven smoothly. So I think that is a safe point because we're not driving the robot to be really fast, and as long as there's no jerking motions or like the fast stopping, then it's fine.
And then for the end of the quarter, our project demonstration plan, we plan to assemble the power system prototype as well as 3D print the grabbers to have a prototype as well to show, functional frame and a functional drive system we also hope to meet by the end of this quarter. But we do not expect to meet the remote controlled product yet. Count on it for the spring.